Hi everyone, welcome to our stream. So I'm going to be reviewing. I've got 10 questions to review, and let me just check my levels and everything before I jump in. And everything looks good. Okay, so basically in this review I'm going to go through everything we've done in the course, and I'll do it in the order that we've done it in the course. There is one calculus question which I will tell you that it's a calculus question, and for the physics 101s, physics 111s, please ignore that. It's only for the physics 101 students. Okay, and then after this live stream is done, I'll try to timestamp all of the questions so you can quickly jump to them. Okay, I've never done that before, but it can't be that hard. Okay, so let me go through all the questions first to see if if there's any questions that interest you or whatever, and then I'll just jump in. Okay, so the first question that I'm going to do is just a couple of conversions. Conversion is extremely easy, so I'll just do a couple. There's really no need to do more. Then I'm going to do one on average velocity. There it is. Okay, and non-calculus version. And then after that, I'm going to do an calculus question here like that, okay, on general kinematics. And again, that is not for the physics 111 students, so it won't take long though. If you're a physics 111 student, just make a coffee during this question. All right, and then after that, I'm going to do a couple of one-dimensional problems. One which is throwing a rock up into the air, the sort of things we did in class. Another one is just a car driving down a straight highway or straight street and coming to a halt. Okay, and then I'll do number 6 here will be an oscillator problem. This is 1D oscillation. Okay, and then I will do some vector problems. What do I have there? 3 vector problems where I will convert from either polar to Cartesian or Cartesian to polar. Okay, I should mention that in my notes I do have the addition of vectors. We will need that later in the course, but I'm not going to test you on that during this test. Okay, and I didn't even ask you any questions on that, but in the future we will be adding vectors. Okay, so I did present it at the appropriate time, but there's no need to overdo things. Okay, and after that, question number 8. Question number 8 is, so I said I was going to go in order. It's slightly out of order. I'm going to do a uniform circular motion first, and then I'm going to do 2 projectile problems after that, okay? And so here's a projectile problem, question number 9, okay? And question number 10 is also a projectile problem, but it's intentionally closely related to 9 because I just want to show you something about a variation that I didn't do in class or in my lectures. All right, so that's what we're going to go over. Let's start off with question number 1 here. And the first question is convert 15 centimeters squared, okay, to MKS units. All right, now MKS units, centimeters are metric system units, okay, but they're not the MKS units for length. Obviously they measure length. The MKS units for length are meters, and so we need to convert centimeters to meters. And the conversion is 100 centimeters is equal to 1 meter. Okay, so here's our conversion right there. All right, there it is. And the reason you need to write it that way is you need to form fractions. And the fraction, there are two possible fractions, pretty obvious, either a meter divided by 100 centimeters, like this. That's equal to 1. The other fraction that you can make is 100 centimeters divided by 1 meter is equal to 1. Because a meter is equal to 100 centimeters, in both of these fractions, the numerator is equal to the denominator. So that means that the fraction is equal to 1, and you can always multiply by 1. Okay, now this is 15 centimeters squared. All right, and so that means that you actually have 2 centimeters there, centimeter times centimeter, like that. And you have to convert both of them. And so you say, well, how do I convert those 2 centimeters? Well, the first one you can convert using this fraction right here. Okay, because that centimeter there will cancel that centimeter there. But you still have a centimeter remaining, so you're going to have to do that twice. Okay, so there you go. You've got this centimeter canceling that centimeter, and that centimeter canceling that centimeter, and your answer will come out in meters squared. Okay, I'll write in the number in just a second, but it has to come out in meters squared because the original was in centimeters squared. Basically, this whole problem is a length squared. So whatever the units are at the end, they have to be a length squared. Okay, so if you just divide 15 by 100 and then divide by 100 again, you will get the following number. Okay, and let me just copying and pasting from my answer over there. Whoops, got that twice. Okay, and that's how your calculator might actually present the number for you. 1.5 times 10 to the minus 3 meters squared, or 0.0015 meters squared, like that. Okay, so there it is. There's the answer. All right, now the next question was just to make life a little bit interesting. We haven't worked and we won't work in inches and feet and pounds and that in this course, but it's not difficult to convert between non-metric system and metric system. All you really need, you always need this fraction right here. Okay, so this is the fraction of equivalency between the one unit and the other unit that you the unit that you're in. So we're in inches. Okay, and you want to go to meters, but this one's in centimeters. So you say, well, what do I do there? Well, you know that centimeters, there's 100 centimeters in a meter, so you could divide this by 100, and that gives you 0.02454 meters. Okay, so an inch is basically the same as 0.0254 meters. Okay, now why? Well, there's 100 centimeters in a meter, so basically you have to move the decimal over. You'd have to divide by 100, and if you divide by 100, you're moving the decimal over 2. That's 1 and then 2, like that. Okay, so this is the fraction we actually want, there and there. Okay, and so down here, 25 centimeters cubed. That's, by the way, a volume. And cube just means you have inches times inches times inches. So there are 3 inches, like that. The little periods there just mean multiplication. Okay, and you need to form the fraction like this. And you say to yourself, well, do I want the inches in the numerator or in the denominator? Well, since these are in the numerator and you want the inches to cancel out, you need to put the inches here in the denominator. Okay, and then of course you'll get the meters in the numerator. Okay, so that's how you decide, which way you want the fraction. And what does this say? This says that 1 inch is exactly the same as 0.0254 meters, like that. Okay, now that'll cancel one of the inches. All right, but you have 3 of them, so you have to do this 3 times. Or you could just write, actually, you could just write cubed, like that. Okay, because after all, you go back to the way it was originally written, cubed, like that. So you have 3 inches here, and so you have to convert all 3 of those, and that's why you have that cube there, like that. Okay, and let me just give you what that answer is. I've got it both in scientific notation and not. So if you just did it on your calculator, you might get a bunch of digits like that. Okay, in scientific notation, you would move the decimal over 1, 2, 3, 4 to the right, and so that's 10 to the minus 4, like that. And so 4.10 times 10 to the minus 4 meters cubed. All right, there's our first question done. All right, should be easy enough. All right, we're going to move on to the next one. And let me see. Okay, we've got 4 people in in the chat there. If you have any questions, you just type them into that text chat on the side, and I'll take a look every once in a while. Now, there is about a 15-second delay, so just be aware that I won't answer your questions right away, but I'll probably do to the end of a question and then look over at the chat and see if there's any questions. And if you have any other questions that, like, you have any other problems that you want me to do, I can always insert problems in the middle. You might say, look, I want to see another harmonic oscillator. I could do that. Okay, let's go on to our second one. So the second one has to do with average velocities. This is like our one of our first lectures. Okay, a glider on a linear air track, and you might have seen these already in the lab. Okay, so you've got a glider on a linear air track, and it's found to be at the following positions at the corresponding times. Okay, and so you get this chart here, and here's the time, and here's where it is. Okay, from some reference point, I didn't draw a picture, but at 0.25 seconds, it's at 3.75 meters from some reference, from the origin, okay? And then at 0.5 seconds, it's at 3.95 meters. At 0.75 seconds, it's at 4.05, and at 1 second, it's at 3.9 meters, okay? From the origin. All right, now I've got 4 questions here. The first question is, what is the average velocity between 0.25 and 0.5 seconds. So whenever we're talking average velocity, you can't say what's the average velocity at a particular instant in time. It always has to be during an interval, okay? So what's the average velocity between 0.25 seconds and 0.5 seconds, all right? And the way that's calculated is using this formula right here. I'm going to do that. And cut and paste it. Okay, it's using this formula right here. It's basically your change in x, your change in position, divided by your change in time, and that'll give you the average velocity. Now, in class, we wrote the average velocity as a v with a line on top of it, a straight line on top of it. I can't do that in my text editor, so I just put the curly brackets there like that. You might have seen this in like a stats class or something if you've taken statistics, and that just means average. That's all it is, okay? So the average velocity is basically your change in x divided by your change in time. Okay, so what's your change in x? Well, what I've got highlighted there is your beginning and end point. So here's the end point, and you always do the end point first. So you've got 3.95, okay, minus 3.75. That's your delta x, okay? So once again, 3.95 minus 3.75. There it is, 3.95 minus 3.75. There's your delta x. Your delta t is your change in time. So it's always the final time minus the initial time. The final time was 0.5, the initial time was 0.25, and there it is in the denominator, 0.5 minus 0.25. Now, if you calculate this, so it's a fraction, and I'm sorry, in the text editor, I really can't do the fraction like one number over top of another, but this is the numerator. There's the denominator, and if you just work that out in your calculator, you get 0.8 meters per second, okay? And it's got to be positive. Let me put the positive in there, because x is increasing. You see, you started at 3.75 and you went to 3.95, so you're moving the positive x direction, okay? And that's why the velocity has to be positive, all right? Now, the rest of these are easy, so I'll go a little bit quickly. I'll just cut and paste the answers here. Like that, okay? Basically, it's the same formula, but now applied to different numbers, okay? So let me show you how I substituted in the numbers there. So this is delta x, but it's between 0.5 and 0.75. So now we're looking at those pairs of numbers, or those pairs of positions, okay? So for the delta x, it's the final position minus the initial position, 4.05 minus 3.95. There it is. 4.05 minus 3.95, minus, in the denominator is delta t, and your delta t is 0.75 minus 0.5, like that, and that works out to 0.4 meters per second, okay? So it's slowed down a bit. It was going at 0.8 meters per second, now it's going at 0.4 meters per second. And the next one I ask you is between 0.75 and 1. So that's the last pair here, okay, between 0.75 seconds and 1 second. And again, I'll just cut and paste that answer because the actual math here is pretty simple. The delta x is the final, which is 3.9 minus the initial 4.05. 3.9 minus 4.05, okay? And you can see that that'll turn out to be negative. And that's because it's now moving back towards the origin. So x is decreasing and the velocity is actually negative. All right, so there's the numerator, there's your delta x, okay, there, okay. And your delta t is 1 second minus 0.75 seconds, 1 second minus 0.75 seconds, and that gives you a velocity of negative 0.6 meters per second, okay? Now, the next question, it's the same thing again, but I wanted to show you, I wanted to try to give you an understanding of how these average velocities here relate to instantaneous. You can see that these first three questions were like as close, were over time intervals that were as close as possible, like quarter of a second time intervals, like from 0.25 to 0.5, sorry, and then from 0.5 to 0.75, and then 0.75 to 1, like that. Okay. The last question was, was what is the average velocity between the initial time 0.25 and the final time 1? In other words, what's the average velocity from this one as the beginning point and that one as the end point? Okay, skipping the middle points in between. And the formula is the same, but you'll see that the answer is kind of interesting. So here's that answer right there. So the delta x is all the way across the entire interval. So from that's your final position at 1 second, 3.9, and that's your initial position at 0.25 seconds. So 3.9 minus 3.75, 3.9 minus 3.75, okay? And that's your delta x. Your delta t is your final time, 1 second minus 0.25 seconds. And you can see here, that's 1 second minus 0.25 seconds. And you're going to get an average velocity of 0.2 meters per second, okay? Now, the reason this is interesting is because you could actually get that answer in a different way. You can get that answer this way. Look at what your time interval was during the first quarter of a second. Okay, it was this, 0.8. Let me write that down here. 0.8. Whoops. Copy, paste, there we go. All right. And then during the second time interval, it was 0.4 meters per second. And then during the third time interval, the third quarter of a second, it was that, okay? Now, if you add all those together and you divide by 3, and you might say, why 3? Because there's 1 time interval, there's 2, there's 3 time intervals. So you take all the velocities during those 3 time intervals, and then you divide by 3, guess what you get? 0.2 meters per second, which is exactly this answer here, okay? In other words, the average over the full period is equal to the average of the averages during the first third, the second third, and the third third, which is what you would expect, okay? And, you know, because after all, it is an average. It's just that this is an average over these averages. And so it works out. Okay, that should give you some intuition. For the instantaneous velocity, what you would do is you would make these delta t intervals smaller and smaller and smaller. But we can't, because the smallest you can make them from the data is 0.25 seconds. You can see from 0.25 to 0.5, that's a quarter of a second, and then there's another quarter of a second, and then there's another quarter of a second. So that's the smallest we can make delta t. So when I ask here, what is the instantaneous velocity at 0.95 seconds, you can't answer that question, okay? Why? You just don't have that data. First of all, you don't have any data at 0.95 seconds, but even if I said what is the instantaneous velocity at 1.0 seconds, you can't get that because you don't have a delta t around 1 second, which is very small, okay? So we can't answer this question, all right? So instantaneous is at an instant, and it comes out of these averages by making delta t smaller and smaller and smaller, okay? And we just don't have that data. All right, so there's another way you can actually get at this question. You see, I ask, at what point in time does it stop moving in the positive direction and start moving in the negative direction? Okay, now we know that it has to, like, at some point switch between positive velocity and negative velocity because we see it happening here. Okay, during the first 0.25 seconds, it's traveling in the positive direction. Okay, and then it continues traveling in the positive direction, and then it's moving in the negative direction. So at some point, it must have turned around. Okay, you might be tempted to say that it turned around at 0.75 seconds because you can see that that's the furthest it goes in the positive direction, but you don't know if after 0.75 it continued moving in the positive direction or if that was it. Okay, and so you really can't tell whether or not, or it might have even gotten further into the positive direction at an earlier time and then was already starting to move back towards the origin. So you can't tell just from this data at what point it stopped. You could guess, you could guesstimate and say roughly around um, 0.75 seconds. And you go, well, where did you get that number? When you take a look here, you can see that that's the furthest in this data that it goes in positive x, say to the right, and the other two numbers, like at 0.5 and at 1 second, they're closer to the origin. So you might say, well, it looks like it's around 0.75, but you can't say for sure. Okay, you just don't have that data. All right, so that's about all we could do with average velocities. I'm not going to ask a question on average acceleration because to get average accelerations out of average velocities requires a level of sophistication that I don't want to get into. It requires some numerical analysis that is beyond really what we want to do in the course. Though it will, there is a way of doing it, and the computer in the in your lab, where you're looking at accelerations along the glider along the linear air track when it's slanted, it will actually calculate average velocities, and it's calculating those from calculate average acceleration, and it'll calculate that from average velocities, but it's kind of tricky to how that's done. Okay, so that's enough for that question. Let's see if there's any questions in the chat there. No one has typed anything. Let me just type something in the chat so people can see where you can type there. So ask questions here, exclamation point. Okay. All right. So let's go on to question number 3. Now, if you are a Physics 111 student, just give me about 5 minutes. This is a fairly short question, but it's only for the Physics 101s, okay? And for Physics 101, if you have data, you can't make delta t infinitesimally small, okay? Because the delta t is the smallest that your intervals are in your data. But mathematically, you can make your delta t infinitesimally small. And if you keep making delta t smaller and smaller and smaller, this average velocity here, okay, let me write it down here. This average, whoops, I didn't copy and paste properly. This average velocity here, when you make delta t an infinitesimally small, it turns into a derivative. And then you have an instantaneous velocity like that. Okay, sorry, excuse me. I didn't mute in time. I tried to mute if I sneeze, but okay. Anyhow, all right, so it turns into a derivative, okay, and that's the velocity. And then if you want to get the acceleration, it's also an instantaneous, but this time it's the derivative of the velocity with respect to time, okay? So basically what I'm giving you in this problem is I say, look, the position of an object as a function of time is given by this formula right there, okay? And it's a fourth order. So there's a fourth order term, so there's a t to the fourth, there's a t cubed, there's a t squared, a t, and then a linear term. Okay, sorry, I mean a constant term, minus 10, okay? And I ask, what is the position, the velocity, and the acceleration at these times, okay? Well, the first thing to do is we have already the position at all times. Let's get the velocity at all times. So what you want to do is you want to differentiate this formula here. And you just go term by term. The derivative of 4t squared is, the derivative of t to the fourth power is 4t to the third power, okay? So t to the fourth power derivative is 4t cubed, and then we have minus 5 there, like that. And then over here we have t cubed, and the derivative of that is going to be 3t squared, like that, and we're multiplying these numbers here like that, okay? And then we have plus 2 right there, and the derivative of t squared is 2t, so we multiply that by 2t like that. All right. And then the derivative of plus 5t is just plus 5. And that simplifies down to, here, let me just cut and paste the answer. Simplifies down to this. Okay, so there's our velocity as a function of time. Okay, and then we differentiate this again to get the acceleration as a function of time, and start with this term right there. And so we have a 4 multiplied by the derivative of t cubed is 3t squared, okay, minus 15, and derivative of t squared is 2t. All right, and then the derivative of 4t is just plus 4, there, like that. And that's it for that one. And let me just cut and paste the simplified answer there like that. There we go. Okay, so that's your acceleration as a function of time. Okay, well, now what? Well, the question was, what is the position, velocity, and acceleration at t equals 1.5 seconds? Okay, and so you want to take, let's do the position first. You take the position here, and wherever you see time, you put 1.5. Okay, so wherever you see time here, you put in 1.5, time here, 1.5. Oops, what did I do? I missed that. Okay, and then time here, 1.5, and then time there, 1.5, like that. Okay, and so 1.5 to the 4th power minus 5 times 1.5 to the 3rd power plus 2 times 1.5 squared plus 5 times 1.5 minus 10, and that number is equal to, I'm sure you can do this on your calculator, so I'll spare you the details. You just get this number here, okay? Negative 9.81250. Okay, now on the test I would just round that off to 3 significant figures, but there it is. There's the answer to more significant figures than we need. Okay, what about the velocity? There's the velocity as a function of time. In every place you see t, put in 1.5, 1.5, 1.5, and 1.5. Okay, and then you just crunch that through your calculator, and you will get a number. You will get that number right there, negative 9.25. And then finally, the acceleration as a function of time, calculated at 1.5 seconds. Okay, there, just put in 1.5 for all of those t's, and you're going to get the answer, negative 14, like that. Okay, so did we answer the question? Well, the question was, given that position function, calculate the position, velocity, and acceleration at 1.5 seconds. And this is the position at 1.5 seconds. Okay, I didn't give you units here, but assuming they're MKS units, that would be meters. So that would be like on the negative side of the axis, negative 9.81250 meters. Okay, and then the velocity here would be negative 9.25 meters per second, and the acceleration would be negative 14 meters per second squared. Okay, and that answers question number 3. All right, for the Physics 101 students. All right, end of the question. Let me check the chat here. All right, no one seems to be asking any questions, and so I'll just continue with question number 5. All right, or sorry, question number 4. All right, okay, so question number 4 is a 1D problem. So let's read it carefully, and we'll draw a picture too. I throw a rock upward with an initial velocity of 20 meters per second. Okay, when it passes by a window, it is traveling at 10 meters per second. Okay, I guess I should probably just say up, still up. Okay, so let's read that again. I throw a rock upward with an initial velocity of 20 meters per second. Okay, and beside a building, And when it passes by a window in the building, it's traveling at 10 meters per second up. Okay, and the first question is, how high is the window above me? All right, that's the first question. And the second question is going to be, how long is it in flight when it leaves my hand until it passes the same window on the way down? All right, so let's read the questions again. How high is the window above me? Okay, because the rock is leaving my hand, so it's leaving my hand at 20 meters per second. It's going up, and as it goes up, it slows down. It passes by a window 10 meters per second as it passes by the window. And the first question is, how high above me is the window? And the second question is, how fast is the rock, or how long is the rock in flight when it passes, from the time when it leaves my hand until it passes the window on the way down? Think about it. The rock is going to go up, and then it's going to come back down. It's going to pass the same window on the way down that it passed on the way up, and I want to know how long that time of flight is. Okay, so it's worth drawing a picture, and so let's switch to this here, and what do we have? Okay, so there's a building, and I don't know how high the building is. It doesn't really matter that much. Okay, and there's a window here like that. All right, and I'm down here at ground level. I won't draw me, but there's the rock in my hand at ground level. And what I do is I throw the rock up, okay, and it goes up, 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 and then eventually comes back down like that, okay, and it hits the ground. All right, okay. The first question is when it's passing the window on the way up here like that, okay. All right, so that's part A, is when it passes that window there. Well, before we start, choosing where the initial and final is, the next step past this, after you draw a picture that sort of depicts what's going on physically, is to draw a coordinate system. Okay, now this is a 1D problem, and so we don't need an X and a Y. We just need like an X. I could have called it Y because it will be vertical, but we called it X when we did 1D, so I'm going to continue calling it X. So it's just straight up like that. That blue line is my x-axis, and I'm going to take positive up as being positive, okay, and then I got to choose an origin. And you say, well, where do you want to choose the origin? It kind of makes sense to choose the origin at ground level here, or actually you can even say where the ball is in my hand, or the ball, I mean the rock. Okay, so there's my x equals 0. There's my origin. Okay, all right. Okay, now for part A, let me switch back just for a second here. For part A, let's think about what the initial and final positions are here, or where the initial and the final are. How high is the window above me? Okay, so the rock initially starts at ground level, because I'm at ground level, with this initial velocity of 20 meters per second, and then it gets to the window. Those are the 2 points that are of interest. Okay, so for the initial we will choose down here. This will be our initial. I'll just put an I there like that, and our final will be right there. Okay, the ball, I keep saying ball, the rock is still moving up. Okay, for part A, and that's the final. Okay, and now you can read off the quantities off of this graph here. Okay, so initially you could say, well, what's its initial position? Well, its initial position is 0, right, because it's at ground level. So there's I, and X means initial, position. The naught means initial, so the initial position here is basically 0. The final position, we give it the symbol X, but we don't know how big that is, how high that is, and that's in fact what we want to find. Okay, and we have an initial velocity. It's 20 meters per second up, like that. Okay, so I've got a little positive there like that. Okay, and the final velocity, that's the velocity when it passes the window. Again, this word final is probably not the best word there. It's the point of interest. Okay, so we're only interested in the motion up until it's passing that window, so that's why we call it final, I guess. And that's going to be, it's still moving up, so it's still positive 10 meters per second. Okay, so you've got here initial and final position. We have here initial and final velocity. And then the only two other quantities are the acceleration, and that's going to be negative 10 meters per second squared. All right. The acceleration is which way? It is down, like that, right? That's gravity's pulling you down. Okay, and and then of course the time, and that's the time it takes to go from the initial to the final. We don't know that time. Okay, so that's what we have so far. So from the graph, the picture and the ruler there, the line in blue, that's what we have. Okay, so with those numbers, we can try to plug into our 1D kinematic equations for constant A. And let me just cut and paste all those. All right. So, hold on here. So here are our equations. All right. Okay, good. They showed up. Okay. And let me just cut and paste the quantities that we determined from the picture. Okay, so these are exactly what I wrote just a minute ago in the in that picture that we drew. Okay, and now you take a look here, and maybe I should just give these a name. These equations. This we called equation number 1. This one we called equation number 2 in the notes, and this one we called equation number 3, like that. Okay, so you take a look there and you go, okay, what am I trying to get? Well, you're trying to get x, okay? That's like how high the window is, all right? And that tells you either want equation number 1 or you want equation number 3. And then you take a look at the time there and you go, oh, I don't have time. I'm not asking you for time, but you don't have time. And without time, then equation number 1 is no good. Okay, so we have to really use equation number 3. Okay, so let me reason through that again. What are we trying to find? We're trying to find x. That's why I put 3 question marks there. That's the not only unknown, but what we're trying to find. And so there's only 2 equations that have x in it. There's x there in equation 3, and there's x there in equation 1. Okay, so equation 2 is out. And then you take a look at equation 1 and go, we're trying to find x. And you could try plugging into it, but I'll tell you what will happen. You get to time and you go, oh, I don't have time. And so you say, well, equation 3 had better work, otherwise we can't solve the problem. And it does. Okay. So there's equation 3. I just rewrote it. And so for v, it's 10, like that, squared. All right, so I substituted in there for v squared. And for v naught squared, v naught is 20. So we're going to have 20 squared like that. Okay. And then we have plus 2. And for a, we have negative 10. And then we have x minus x naught. But x naught is 0 because it starts at the origin. Okay. So if we simplify this, we're going to get 10 squared is 100 is equal to 20 squared is 400. Minus 2 times negative 10 is 20, x, like that. And that gives me that x is equal to 15 meters. Okay. And that answers the question. All right. So how high is the window above me? It's 15 meters above me. Okay. All right. So part B was how long is the rock in flight from when it leaves my hand until it passes the same window on the way down? Now this on the way down is kind of a clue here, which is why I said here, traveling 10 meters per second still in the upwards direction, because now we've actually got a slightly different situation. We actually have it coming down. Okay, so remember, whenever you have part A and part B, be careful that I didn't change either the initial or the final points, because if I did, then you have to rethink it. Okay, it's not that bad, but you do have to rethink it here. Okay, so here's our picture, and for part A, the final was here. Okay, this was for part A. All right. For part B, that's on the way up. So maybe I should put some little arrows here. See, that's like the rock is moving up. The rock is moving up here like that. Rock is moving up. The rock stops right there at the top, and then it starts to come back down, starts to come back down. And then, of course, it passes by the window on the way down. And let me use a different color here. On the way down, this is where it passes the window on the way down, okay? Right there. So this is our new final, okay? And what changes? Well, these stay the same. Well, actually, not quite, not quite. The X value, we now know how high that is. We now know that it's 15 meters above above me, okay? So now from part A, we can say that the window is 50 meters above us, okay? So one question mark has been resolved, but we have to rethink these ones, okay? What about those two? Is the initial velocity still 20 meters per second? Yeah, sure, because, you know, I didn't move, you know, it's not like I'm throwing it a second time. So it's still 20 meters per second. But now that plus 10 meters, that was on the way up. On the way down, it's not plus 10 meters per second. It is minus 10 meters per second, okay? So be careful, that's what changed right there. That one right there changed. Okay? The acceleration is still negative 10 meters per second squared, and the time is also unknown, okay? We didn't calculate any time information, so that's unknown, okay? So just be careful, you know, on the way up, it was plus 10 meters per second, but for part B, it's on the way down, so it's minus 10 meters per second, okay? And so let's switch back to this here, all right? And so for part B, let me just cut and paste my answer here. Don't want to waste your time watching me just, you know, type things out. So find to find the time, how long, find time, how long before it passes the window on the way down. Same values as above, except that, as I said, V is now negative 10. And we can use equation 2 right now, okay? Because we're looking for time, and we do have both the initial and final velocity, and we have the acceleration. So if you take a look at number 2 here, we have the initial velocity, that's v naught, that's 20. We have the final velocity, negative 10. We have the acceleration, which is also negative 10 meters per second squared, and we're trying to solve for t. Okay, so we can use that equation here. Let me just cut and paste it so you can see how I substitute it in. Oops. All right. Here we go. Okay, so the final velocity, v, is negative 10. It's moving 10 meters per second down when it passes by the window. The acceleration due to gravity is still negative 10 meters per second squared. And the time is unknown. And the initial velocity is 20 up, positive, okay? And so just solve for that and it gives you 3 seconds, okay? So basically, it takes 3 seconds from when I throw it until it starts to come down and passes that window on the way down. Let me just, you know, demonstrate that for you. So, you know, starts down here. I mean, let me use red, I guess. Starts down here, okay? And, you know, tick, 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 tick. You know, eventually gets up here. It hasn't quite reached 10 seconds yet. Sorry, 3 seconds yet. Okay, and then by the time it gets to that final right there, okay, that's 3 seconds. Okay, so it passes the window on the way down after 3 seconds. All right, so that answers that question. Let me see if there's any comments in the chat. Nope. All right, if there are no comments, I'll just wait a second. All right, if there are no comments, let me move on. Question number 5. Okay, so we're doing pretty good with time here. Yeah, I think maybe I'll get this done in under 2 hours. Okay, question number 5 is also a 1D problem. Okay, I'm driving my car at 30 kilometers per hour. Okay, which is a bit slow. You know, like 30 miles an hour is like 50 kilometers per hour. So I'm just doing like 30 kilometers per hour. Okay, and I'm going to guess that's like about 20 miles an hour. Okay, like maybe like in some of the school zones or something like that. All right, and I hit the brake. Okay, hit the brakes. Okay, so I'm driving and I hit the brakes. The car comes to a halt in 100 meters. Okay, so I want to ask two questions. The first question is, what is the deceleration of the car? And part B is, how long does it take me to stop? Okay, now you got to watch this word deceleration. Basically, deceleration and acceleration are the same thing. We use the word deceleration whenever the velocity and acceleration are in opposite directions. Okay, so it's just like, you know, how that English word works. Everything is still acceleration. It's just that we tend to call acceleration deceleration when the velocity and the acceleration are in opposite direction. That's because the velocity is moving you this way, but the acceleration wants to go in the other way, so it's slowing down, slowing down the velocity. Okay, so whenever the velocity and the acceleration are in the opposite direction, the velocity is still going in the same direction, but it's decreasing. Okay, and we tend to call that deceleration. You're slowing down. Okay, so there it is. All right, so let's draw a picture for that. Okay, let me go here and create a new. Okay, good. Do you have a whiteboard? You do. All right, so you know, we have a road here. Let me do that in black, like this. Okay, and there's a car. My car is over here to start with. So there's my initial. All right, and not a really detailed picture, but you know, at some point the car gets to here and the car has stopped. Okay, like that. Now, we can even say something like, we can even put the values on this diagram here, rather than writing them off to the side. But before we do that, we need to have a coordinate system. There it is. There's my plus x-axis there, like that. Okay, and here's my origin. This is where I first start to brake. Okay, right there. All right, so I first start to brake right there. We can even put a little x naught. So I start braking right at the origin, and then I come to a halt, and you say, well, do I know how far I travel until I come to a halt? Well, we can reread the problem. It says, I'm driving my car at, okay, 30 kilometers an hour, and I hit the brakes. I come to a halt in 100 meters. Okay, so if I started to brake right at this point here, right at the origin, then I come to a halt in 100 meters. How far did I travel here? 100 meters. Okay, now I came to a halt tells me that at the velocity at this point here is 0. There you go, I've come to a halt. And what's the velocity over here? It's some initial velocity. And I tell you that I'm originally traveling at 30 kilometers per hour. Okay. Now 30 kilometers per hour, that's not MKS. We'll convert that in a minute. But there it is. You have your initial position and velocity. You have your final position and velocity. And then the only other two quantities are the acceleration. Okay. And we don't know what that is. In fact, if you go back to the question, I say here, part A, what is the deceleration of the car? Whenever you see the word deceleration, solve for the acceleration. Deceleration just means that A and V should have opposite signs, and we'll see that that turns out. But, you know, don't let that word deceleration throw you off. It's not some other thing. It is just the acceleration. Okay, so we don't know what A is, and we also don't know the time, how long it takes to come to a halt. Okay, so those two are unknown. All right, so go back here, and let me get rid of this statement here. Let me cut and paste the quantities that we just determined. We determined that its initial position, this is from the picture, the initial position was 0 meters. The final position was 100 meters. Okay. The initial velocity was 30 kilometers per hour. I'll convert this in just a second. And then the final velocity was 0 meters per second because I come to a halt. Okay, didn't know the acceleration and didn't know the time. All right. Now, how do you convert this to MKS? And you have to. If you don't, your answer will come out in very strange units. And the reason is because you see, this is in meters and this is in kilometers per hour. And, you can't mix kilometers and meters without getting a mess. Okay. So the usual rule is always convert to MKS before you plug into the equation. Then the answer will come out in MKS. And converting from kilometers per hour to meters per second, we've done that a few times. It's just as easy as dividing by 3.6. And you might say, well, why is that? Why does it work out that way? And so I'll do that for you here in case you didn't catch why it works that way. All right. So you have 30 kilometers per hour. So we have to convert the kilometers to meters. Okay. And you've got kilometers in the numerator, so you want to put kilometers here in the denominator, and you want to convert that into meters. So meters in the numerator, kilometers in the denominator, and then you want numbers in here such that it's equal to 1, so that this entire fraction is equal to 1. Well, 1 kilometer is 1,000 meters. Okay? Okay, so, 1,000 meters is a kilometer, so this entire fraction is 1. You can always multiply by 1 without changing a value. The effect of this fraction here is to eliminate the kilometers, because they'll cancel out, and replace them with meters. Okay, but we're not done. We also have these hours. Now the hours are in the denominator, so we'll put them in the numerator over here so that they cancel. You see the hours in the denominator here, cancel the hours in the numerator there. And we want to convert to seconds, so we'll put the seconds in the denominator. And you know that, there's like 60 minutes in an hour and 60 seconds in a minute. And if you do 60 times 60, you find that 1 hour is the same as 3,600 seconds. Okay, now the units will cancel out. And so you're going to get, your final units here. Let me write them over to the side here. Will be meters per second, because that kilometer there will cancel that kilometer there, and that hour there will cancel that hour there. And then you'll just get meters on top and seconds on the bottom. There they are. But then you go, well, what about the number? Well, you got 30 multiplied by 1,000 divided by 3,600. Okay. And it'll always come out to be this fraction. When converting from kilometers per hour to meters per second, you'll always get this fraction 1,000 divided by 3,600. Well, we could just do that division once and for all, and so it's just like dividing by 3.6. Okay, so whenever you see kilometers per hour, if you just want to save yourself time, take the kilometers per hour, divide by 3.6, and you'll get your answer in meters per second. Okay, so that's it. That's all you have to do there. And up here, 30 kilometers per hour, divide that by 3.6, it's 8.333 meters per second. I kept a few extra digits there. There's no danger in keeping extra digits while you're doing the problem, but the answers will always assume 3 significant figures. Okay, so what do I have here? I actually have 5 significant figures. Okay, all right, now what? Well, you take a look at what you have. Take a look at what you're solving for. You're solving for the acceleration. So this is what we're solving for right here, part A. Okay, and you go, all right, well, take a look at these equations here. We're solving for A. That means either we want equation 2 or we want equation 3. Okay, with A. No, actually, all 3 of them have A in it. Okay, but we don't have time, so you can't use number 1 and you can't use number 2. So we will use number 3. Okay, so over here, you use number 3 because it's the only one. See, we don't have time, so it's the only one that doesn't have time. And then substituting in, the final velocity is 0 squared. So there's v2 squared right there. That's going to equal v naught, which is in MKS 8.3333333 squared like that, plus 2 times, we don't know A. Okay, and I wanted to do a problem where we had a car driving, because when you throw things up and down, the acceleration is always negative 10 meters per second squared. It's always 9.8 rounded off to 10 down. Okay, but that's not the only time you might have constant acceleration. This is an example where you have constant acceleration when you hit the brakes, and that's a pretty good approximation. When you hit the brakes, you're slowing down, and you're slowing down at a constant rate. Okay, so that's a constant acceleration. Or when you step on the gas, at least at the beginning, that's a constant acceleration forward. Okay, so cars will have constant accelerations when they change speed, but it's not 9.8. So don't make the mistake of thinking that the acceleration is always 10 meters per second squared. It isn't. It can be different. And in this case, what is it going to be? Well, let's finish off here. So v squared is 0 squared. V naught squared is 8.3333 squared. 2a, we don't know a. X minus x naught. X was 100. Minus x naught was 0, like that. And that just gives us 0 is equal to... you know what? I'll just give you the answer because it's not hard at all to solve. Basically, it just works out to this value right here. Okay, so I don't know if you want me to 0 is equal to whatever that is squared. Oh, I don't have my calculator ready. Sorry about that. Just give me a second to bring that up. Oh, missed. There we go. Plus 2 times, actually 200, because it's going to be 2 times 100, 200a, like that. Okay, so all I did here was I simplified that, and simplified that, and then bring the 69.44 to the other side, divide by 200, and you get that number there. Notice that that number is less than 0, so a is negative, whereas the velocity is bigger than 0. Okay, the final velocity is 0, but until you stop, you've got a positive velocity, and whenever you have acceleration in one direction, okay, acceleration in one direction, velocity in another direction, you have deceleration. Okay, well, that was part A. All right, what is the deceleration of the car? And another one is, how long does it take me to stop? Okay, so how long? For part B, we're actually looking for the time here. Okay, part B. Okay, so now you can take a look at those three equations. Let me scroll back up to them. I missed. Here we go. Those three equations right there. And we're just going to look and say, well, which one will give us time? And it can't be number 3. So it's either 1 or 2. And just by fooling around, you would see that number 2 has enough information. Okay, so you could use number 1, but it's annoying because you've got a square in there. But number 2 is sufficient. So over here, we will just, let me cut and paste that answer for you. For part B, we'll use equation 2. Okay, so maybe I could say part A here. We used v squared is equal to v naught squared plus 2a x minus x naught. And for part B, use equation 2 like that. Okay, and I guess here, use equation 3. All right, so part A, we used equation 3. Part B, we'll use equation number 2. There it is. Substitute in the final velocity 0. The acceleration, we now know it. Okay, it's that value there. Time, we don't know. Initial velocity is that 8.3333. And this is easy to solve. It just turns out to be 24 seconds. Okay, so it takes me 24 seconds to come to a halt. By the way, this is a fairly gentle deceleration. Okay, you would feel it. You feel any deceleration or acceleration in your car, but it's not at all like a jolt. Okay, I don't know how fast a car can decelerate, but if you hit the brakes hard enough, you know how you feel you're being thrown forward. That's because the car is decelerating, and you want to keep going at the same velocity, but you're being slowed down, and so you're being pulled back, into your seat with your seat belt or whatever's, or your steering wheel, whatever's bracing you from moving forward. Okay, so I'm gonna guess maybe like 2 or 3 meters per second squared, you would definitely start to feel your acceleration. It can't be 9.8. That's like as if you were falling. That would be a really big deceleration. Just to give you an idea, like if you want to know, is my acceleration big or small, just compare it to G. Just compare it to like 9.8 meters per second squared. Okay, there is question number 5. Let me see here in the chat. No questions. All right. Let's go on. So we're on question number 6, and we have 4 more questions to go. This one should be fairly short. This is an oscillator. I can even say a 1D oscillator. Okay, so we really haven't done multiple dimension oscillators. There are oscillators in 2 and 3D. They're fairly complicated things, but we're just going to do 1D oscillators. So a 1D oscillator, so it's kind of redundant to say 1D here, but all oscillators are 1D for us. Okay, so an oscillator is found to have a maximum velocity of 15 centimeters per second and a maximum acceleration of 35 meters per second. Okay, this is similar to the assignment problem. Some people had problems with it, so I'm going to go through it. The numbers are different, but it's the same, roughly the same procedure. And so I give you the maximum velocity as 15 centimeters per second, and I give you the maximum acceleration of 35 meters per second. Okay. By the way, a minute ago I said, is this big or small? Like, what would you compare your acceleration to? And if you compare it to g, which is 10 meters per second squared, okay, g is acceleration due to gravity. So acceleration due to gravity is 10, and this is 35. So this is like 3.5 times your acceleration due to gravity. This is a pretty big acceleration. Okay, so quite a bit of acceleration. And the first question is at what point in the cycle do each occur? In other words, at what point in the cycle does maximum velocity occur, and at what point in the cycle does maximum acceleration occur? And the answer is, for maximum velocity, occurs at equilibrium. Okay. Also, what we've been calling x equals 0. Okay, x equals 0 is the equilibrium. It's the center of the oscillator. Okay, and the maximum acceleration, where does that occur? The maximum acceleration occurs at the endpoints. I.e. the amplitude. That's x is equal to either positive or negative a. Okay, now why do I say positive or negative a? Because the whole oscillator is symmetrical. Okay, it might be worth drawing a quick picture here. So if you have an oscillator that's oscillating back and forth, let me just draw the axis first. Been doing axes in blue, so let's do that. Okay, and this oscillator's oscillating back and forth like this. Now I know it should be 1D, but if I drew this as 1D, it'd be hard to really picture things. And x equals 0 is the equilibrium right here in the middle. So there's your equilibrium. And it's symmetrical, meaning that it goes as far to the left and to the right. So the amplitude, this is over here, would be x is equal to positive a. And over here would be x is equal to negative a. Okay. Where does zero velocity occur? Zero velocity occurs right there. That's where v is equal to 0 right there. Oh, no. That's where, I apologize. That's where v is equal to v max. Okay. So v max occurs right at the equilibrium. By the way, where's v0? At the turning points right here. That's where v is equal to 0. So v is equal to 0 there. I know the question doesn't ask that, but since we're covering this, v is equal to 0 there. Okay. Well, what about the acceleration? The acceleration is maximum at the endpoint. So you get a max here at the endpoint, and you get a max here at the other endpoint. Okay. And the acceleration right in the middle is 0. Okay, so you can see that the acceleration and the velocity do the exact opposite. So for the velocity, you get maximum at equilibrium, but for the acceleration, you get 0. And at the endpoint, you get maximum acceleration, but you get 0 velocity. All right. So I think we've answered that first question. Maximum velocity occurs at equilibrium. Maximum acceleration occurs at the endpoint. Okay. Then question B is, what is the period and amplitude of the motion? And you might look at that and you go, well, I don't have any formulas where I can get the period out of maximum velocity and maximum acceleration directly. But you can combine two equations, and these are the two equations that you can combine right there. Okay, you can combine those two equations, and if you combine these two equations, you can actually solve for omega. Okay, so how do you do that? Well, what you do is you simply take Amax. I'll get rid of that and in there. Just take that equation and divide it by that equation. Okay, so you would get basically this. Start off with Amax and you divide it by Vmax like that. And you go, what's that going to give me? Well, take a look at what would happen. If I've got Amax here, that's on top, and if I've got Vmax on the bottom here, like that, what do we get when we divide those two? Well, the A's cancel, okay? And one of the omegas cancel, okay? And what you're left with is just omega. And omega is equal to Amax divided by Vmax. Whoops. There we go. Omega is just equal to Amax divided by Vmax. All right. And again, that just comes out of combining those two equations. All right. Now, you say, well, I didn't ask you for omega. I asked you for the period. I know, but there's another formula. You should always remember that the definition of omega is basically 2 pi over the period. Okay. Let me cut and paste that like that. Okay. 2 pi divided by the period. So, once you get omega, you can use this formula to get the period. Okay. And by the way, you could rearrange this formula here. If you multiply both sides by t and then divide both sides by t, you could rewrite it as the following. Okay. So that all I did to go from here to here was I just isolated capital T. So I multiplied both sides by t. Maybe I'll just put in maybe the intermediate step here so you can see what I did. Take that equation, multiply both sides by t. What am I going to get? I'm going to get this equation. Whoop. All right. So take that one, multiply both sides by t, and I get that one. Okay, then take this one, divide both sides by omega, and I get that one, and that isolates t. All right, let's do it. So we've got that omega is equal to Amax divided by Vmax, and that's equal to Amax is 35 meters per second squared. Okay. Divided by Vmax, and you got to be careful because what did I say here? Vmax is 15 centimeters per second. So maybe before we do anything else, we should convert Vmax from 15 meters per second, 15 centimeters per second, okay, to meters per second. And that would be just, remember there's 100 centimeters in a meter, so divide by 100. Okay, so there it is. There's the maximum velocity in meters per second. Okay, and when you do the math there, you're going to get that omega is equal to 233 something. Yeah, it's just going to equal this right here. Okay, and the units of angular frequency, so we call it omega. The symbol's called omega. It's the last letter of the Greek alphabet, but the name of it, of this quantity, is called the angular frequency, and frequencies are measured in hertz. Okay, and you say, but I didn't ask for that. I asked for the period. Okay, right there. And I know I asked for the period, but the period is related to the angular frequency by this formula right here. And so we say, okay, 2 and pi is just 3.14159 and some extra digits. We don't need them all. Divided by 2.333333333 like that. And that's going to equal, what is that going to equal? That equals this number right here. Okay? So that's your period right there. Now, what is the period? It's the time for one cycle, which means that the time it takes to start at a point, go all the way around once, and come back to the same point is 0.0269 seconds. Now, that's like close to 300ths of a second. So this oscillator is oscillating very, very fast. Okay, and let me just show you on the diagram here. So if you say, well, how do I define the period? Pick any point. Say you pick this point here like that, where my red dot is, and you say, okay, how long does it take for the oscillator to go all the way around once. Okay, so just follow it around, and as you follow it around, of course your your stopwatch is ticking away, tick 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 tick, and then it gets back to that point again. Okay, it gets back to the original point. The time it took to make one complete cycle, that is your period. Okay, so that answers 1. And then I also asked for the amplitude. So what is the period and the amplitude of the motion? And now you could use any one of these like formulas. There's a lot of them with amplitude. We might as well use this one right here. Oops, I lost the cut and paste. We might as well use that one right there to get capital A. That's your amplitude. Okay, and so capital A will just equal Vmax divided by omega, like that. And if we plug in the numbers, I have that over here somewhere, I get this number right here. Okay, so maybe I should just show the substitution of the numbers. I just went directly to the answer, but Vmax, remember, was this value right here, and omega was this value right here. And if we divide, that's in hertz. I'm putting the units, and I don't have to put the units in because they're MKS, but if you work that out, it turns out to be this number here. Now that's a small number in meters, okay? And so what I did was I actually converted it to millimeters, okay? And there's 1,000 millimeters in a meter, so you would move your decimal to the right 4, okay? So there's the decimal, 1, 2, 3, 4. No, 3. I'm sorry. It's 1,000, so you'd move it over 3. So it's going to be like start there, and it's 1, 2, 3. So it's going to be 0.643, 0.643 millimeters. Okay. All right. There you go. All right. That answers the question on 1D oscillator. All right. Let me see if there's any questions in the chat. Looks good. All right, no one's asking questions. Actually, I think we only have 2 viewers, 2 or 3, I'm not sure. Okay, that's all right. I'm sure people are going to watch this later. Okay. All right, so question number 7 is just 3 convert from vectors, convert vectors. So this first one, let's separate them apart here. The first one is convert from polar to Cartesian. The second one is going to be Cartesian to polar, and the third one is Cartesian to polar. The Cartesian to polar is the harder, okay? So that's why we'll do it that way. And by the way, I have difficulties in my text editors of making my degree symbol a superscript. So when you see 105 and that little O, that's just supposed to mean degrees like that. I think you probably figured it out from the assignment, but just to be very clear about it, okay? So, all right, let's do this first conversion. So remember, I give you R and theta. When you're converting from polar to Cartesian, I give you R and theta, and I expect you to find X and Y, okay? And here are the formulas in the answer, because this one is really simple, so there's very little to explain here. Just concentrate on the formulas first. You have R, you have theta, so if you do R cosine theta, you get X, and if you do R sine theta, you get Y, like that, okay? And so here's where I did those values, okay? So R is 3.5, cosine is 105 degrees, and you get, for your X value, negative 0.906, and for your Y value, 3.38, okay? Now, if you want to check, you say, well, did I do this right? Like typical errors, like you leave your calculator in radians, and I give you degrees or something like that. You go, well, did it work out? One check, it's not a perfect check, but it's a partial check, is just see if you're in the right quadrant. So if you take a look here, 105 degrees, that's more than 90, but less than 180. That puts you in quadrant 2. All right, so that angle there, the angle by itself tells you you're in quad 2. And in quad 2, what should you have? In quad 2, your X value should be negative. Okay. And in quad 2, your Y value should be positive, and it does work out. Okay. So yeah, that number is in quad 2. Okay. So again, not a perfect check, but it's something. All right, great. Let's move on. Let's do the next one, which is Cartesian to polar. So Cartesian to polar, I give you x and y, and I expect you to calculate r and theta. Let's go a little slower with this one because this one is more demanding. For r, you use Pythagorean theorem, okay? And that's basically the square root of x squared plus y squared, like that, okay? Now I can't do the square root symbol, you know, that kind of radical symbol like that. So I'm just going to write out SQRT, all right? A lot of calculators do that. And so there it is. It's the square root of x squared plus y squared. Basically calculate x squared, then add it to y squared, and then take the square root of the sum of the two, okay? And now plugging in the numbers and giving you that answer, it is the following, okay? So, you know, the x value was -5, so you do -5 squared. The y value was -3.5, so you do -3.5 squared. Add them and take the square root, okay? By the way, the when you're doing when you're doing r, you know, the value, sorry, the sign of x and the sign of y don't matter. It's only the value that matters. That's because if you square a negative, you just get the same thing as the positive. So if you'd done 5 squared here and 3.5 squared there, you'd get the same answer. Okay, anyhow, let's go on. The next one is this inverse tangent. Now, I can't do an inverse tangent very nicely in the text editor. So another name for inverse tangent is arctangent. Some calculators do that and some don't, okay? So basically what you do is you take the ratio of the y component divided by the x component, and then you take the inverse tangent. But you might have to add something. Okay, and you say, how do I decide if I have to add something or not? And the question is, what quadrant are you in? So if you take a look at this and you're in quadrant, your x value is negative and your y value is negative, in other words, both are negative, you are in quadrant 3. And in quadrant 3, you need to add 180 degrees. Okay, so that's what you're going to use to calculate the angle. And if I just substitute in and work out the numbers, I get the following. Okay, so let me put that on the next line and put that on another line. Okay, like that. Whoops, too many lines. Okay, so the y value was -3.5. Okay, and the x value was -5. All right, so we get -3.5 divided by -5. Take the inverse tangent of that and you get 35 degrees. Then you have to add 180 to it and you get 215 degrees. And is 215 degrees in quadrant 3? It is. Okay, it's more than 180 and it's less than 270. Okay, so it works out. By the way, if you had forgotten to write that 180, you would have just gotten 35 degrees, and that's wrong. It's like 35 degrees is in quadrant 1 and this one's in quadrant 3. And so you say, well, why doesn't my calculator know to add in that 180 because it's in quadrant 3? Well, your calculator can't possibly know, because take a look at what this is equal to right there. Let me just write it down here. How does the calculator know if you're doing -3.5 divided by -5, or if you're doing 3.5 divided by 5? Okay, see, the negative signs cancel there. And because those negative signs cancel, when you do the arctangent, it can't tell the difference between quadrant 3, which has both the numerator and denominator negative, and quadrant 1, which has both the numerator and the denominator positive. Okay, again, just because that the negative sign cancels between numerator and denominator means that, you know, this ratio y over x cannot be distinguished from, you know, this ratio right here, y over x. You can't distinguish the ratio y over x from the third quadrant and the first quadrant. Okay, as a result, you simply have to say, oh, I know that it's in quadrant 3 and therefore I have to add in 180. Okay, so the answer is basically r is equal to 6.1. Okay, and theta is equal to 215 degrees. Okay, so on the test, you know, just like on the assignment, you would see, you know, basically r equals 6.10 comma, and then I would have theta equals, you know, 215 degrees, and you would see that as the correct choice. Okay, Last one, another Cartesian to polar. And so let's do R first. R is easier because, you just substitute in for X. Oh, there's your X and Y. And there's no worrying about what quadrant you're in or anything like that. And in this case, when you do the square root of x squared plus y squared, you're going to get 2.92 for this one. Okay, so x is 2.5, y is negative 1.5, your r is going to be 2.92. By the way, a little check here. This r value has to be bigger than both x and y. Okay, so is 2.92 bigger than 2.5? Yes. Is 2.92 bigger than 1.5? Yes. Okay, and so it worked. If you ever get an r value that's smaller than either the x or the y in absolute values, never mind the sign, okay? If you ever get the r value which is smaller than x or smaller than y, you did something wrong. Okay, and then finally theta, you have to decide what quadrant you're in here, and this quadrant is 4 because y is negative and x is positive, and if you look at that, that is quadrant 4. And in quadrant 4, you have same kind of formula like this, but actually your adding of 360 is optional here. Okay, and you go optional. Why? Well, because if you don't add the 360, you'll get the negative angle. But the negative angle is okay as long as you interpret negative angles as being measured clockwise, okay? I'm still going to put in the 360 just because it gives you a positive angle, but the interpretation is fine. It's quadrants 2 and 3 that you must add 180, otherwise you get the wrong answer. Okay, so let's substitute in the numbers and see what we get. Okay, and I don't know why I got, that's not right there. All right, let's see what we have here. So we have the arctangent of negative 1.5 divided by 2.5 plus the 360, and there it is there. And this should be, is that right? Let me just quickly check to make sure I didn't make a mistake. No, it looks all right. Okay, so there we go. So there's the answer. All right. 329 degrees. All right, I'm not going to do any more vector problems unless someone wants me to do vector problems. All right, no questions in the chat. Let me move on. Okay, 3 more questions to go. The last 2 questions are going to be the projectile motion problems, this 2D constant acceleration. I'm going to do those last because they're the most involved. And in class, I didn't get a chance to do a uniform circular motion problem. These are so simple that, I mean, I could have probably squeezed one in, but there's not much you can really do with them. It's so uniform circular motion occurs whenever you have an object which is going in a circle. So it's 2D because the circle is 2D. But it's the object is neither speeding up nor slowing down, so it has a constant velocity on that circle. The direction of the velocity is tangential, so it's called tangential velocity, and the acceleration, because you're always turning, is always towards the center, so it's called a centripetal acceleration. Okay, and the formulas for that, maybe I should just quickly give you those formulas so you could see them. Oh no, where do I have them? Oh, I see. Yeah, I've lost my formulas. Okay, so there's this formula. Yeah, I didn't actually write them down. I'll write them down right now. So there's this formula. There's one formula. Here is another formula. 4 pi squared r divided by t squared. And the other one is a is equal to v squared divided by r. Okay, so there are the 3 formulas that you need for uniform circular motion. Okay, just keep in mind, maybe I should draw a picture for this. Just keep in mind the direction of these vectors, because a and v are vectors. Okay, they have a direction associated with them. This is 2D. But you might say, well, what direction do they have? They always have the same direction. Okay, so let me just draw that for you. All right. Okay, so I'm going to try to draw a circle here. May not turn out so good. Oh, not too bad. Okay, not too bad. Circle has a center. There's the center of the circle. Okay, and if I ask you which way is the velocity, well, it depends whether the thing is going clockwise or counterclockwise. Let's say it's going counterclockwise. So here's the object right here, okay, where that blue dot is. And you say, which way is the velocity? The velocity is tangential. So it's like that. Okay, so what's a tangent? A tangent, let me just draw the tangent line. Okay, whoops. Tangent is a line that touches the curve at just one point. Okay, so there's your tangent line. Okay, like that. All right, let me rub that off. And so the velocity is, along the tangent line, but obviously in one direction or the other. Okay, so there we go. That's the direction of the velocity. So it's called tangential velocity. And then the acceleration is always towards the middle. So there's the middle right here. And so the acceleration is always inwards towards the middle. Let me try that again. There we go. Okay, acceleration is always towards the center. Okay, how's that? All right, and you might say, well, which direction is the r vector? Well, the r vector, I mean, I could draw it. It's not that interesting a vector. Let me do that in green. Basically, the r vector starts from the middle and then points out to where the object is, like that. And so you could say, if there, which way is the r vector or the position vector? There it is. Okay, so, I guess I could ask a question like, what direction is A in uniform circular motion? You would have to, say towards the center. All right. The magnitudes of those vectors, okay, so direction is like which way is the vector pointing. The magnitude is just how strong or how big that vector is. Those magnitudes are given by those three formulas. Okay, that's enough of that. So let's read the problem and answer it. There's three questions here, part A, B, and C. So a centrifuge holds a sample 5 centimeters from its axis and spins at a rate of 3,000 RPM. RPM, oops, sorry, hold on, let me scroll that down so you can read it. There we go. RPM just means revolutions per minute. Okay, I'll unpack that in a second. Okay, but what is a centrifuge? Well, if you're in biology or even in chemistry, you know that you put these test tube in these things that spin, and they spin so that they separate out, like blood can be separated out into, its various components by spinning it, or milk can be separated into its various components by spinning it, and these things are known as centrifuges. Okay, so the centrifuge holds a sample 5 centimeters from the axis because it's spinning around an axis, so it's 5 centimeters from the axis. That's your radius. Okay, and it spins at a rate of 6,000 RPM. What RPM means, I didn't give you that in class, but it means revolutions per minute. Or another word for revolution is cycle. Okay, so 6,000 RPM would be 6,000 cycles per minute. Okay, and I want to know, first question is, what is the period? Okay, what is the tangential velocity? And what is the acceleration? Okay, so there are the three questions that I'm asking. First, which is the period? As you might imagine, that's going to come out of this. Okay, that's 6,000 revolutions per minute. Okay, so when you buy these things, they are, the writing says RPM on the side, but just read that RPM as cycles per minute. And the word per is basically division, so cycles per minute, like that. Okay, now we can't work in minutes, we want to work in seconds. So that's the first thing to convert. Let's convert the minutes to seconds. Okay, and you say, well, how do I do that? Well, let's put a little division there. The minutes here are in the denominator, so let's put our minutes in the numerator. Okay, minute. And then of course we want to go to seconds, so we'll put the seconds in the denominator, and you know that 1 minute is equal to 60 seconds. So there you go, that converts it. So what does this now turn out to be? Well, 6,000 divided by 60 is equal to 100 cycles, okay, per second. All right, so you can even write it in English, 100 cycles per second. Okay, what does that mean? That means that in 1 second, okay, i.e., let me write it over here. In other words, it makes 100 turns in 1 second. Well, if it makes 100 turns in 1 second, how long does it take to make just one turn? It makes 100 of them in a second, so it must take only 100th of a second to make one, because after the first turn, 100th of a second. After the second turn, 200ths of a second. After the third turn, 300ths of a second. After the 100th turn, 100ths of a second, and that's 1 second, okay? So something is turning 100 times in 1 second. It takes 100th of a second to turn, okay? 100th of a second for one cycle. Okay, and you say, well, why did I think it, like, why did I come up with that? Why was I doing that? Because that's what the period is. That's exactly what the period is. The period is how long does it take to make one cycle? And the answer is 100th of a second, or in decimal form here, 0.01 seconds, like that. Okay? Ta-da! All right, so there you go, 100th of a second. Okay, that's your period. That answers the first question. All right, go through it one more time, because we're going to be seeing a lot more frequencies as we go on, so it's worth really getting this in your head. If something if something makes 100 cycles in 1 second, then it only takes 100th of a second, the reciprocal of that. It only takes 100th of a second to make one cycle. But the time it takes to make one cycle is the period, and so the time is 100th of a second, okay, or 0.01 seconds. All right, good. That answers our first question. The next one is, what is the tangential velocity? Well, we have to look at what we have. We have the period, okay, t is equal to 0.01 seconds, okay, and you can see, do I have anything else? Okay, and what I want to find is the tangential velocity. Okay, so if you look at the formulas here, you want to find v. So you can either use the first one or the third one. The second one doesn't help because it doesn't have v in it. Okay, so you say, okay, well, what am I going to do here? Go back to the problem up here, and the sample is being held 5 centimeters from the axis. That's the radius. Okay, when this sample spins, it goes in a circle with radius 5 centimeters. Okay, so the other number we have here is r is equal to 5 centimeters, and MKS 0.05 meters, like that. Okay, and so now we have t, we have r, and we want v. We have t, we have r, and we want v. So obviously you want to use this one right here. Okay, so use this one, and just substituting in the numbers. 2 times 3.14159, like that. R is 0.05. T is 0.01. Okay, everything in here is MKS, and that works out to, what did I get? I got this number right here. Okay, 31.4 meters per second. Okay, so there's the answer. How fast is it spinning? That is, what's its tangential velocity? It's going in a circle, right? So it's got a tangential velocity. What is its tangential velocity? The answer is 31.4 meters per second, okay? And then, what is its centripetal acceleration? Okay, so now we want A. You could use either 2 or 3. Both of them have A in it, and we have the values for both of them. But we're just going to use this one. We'll just use number 3 here, like that. Okay, and so we've got, put this on the next line, A, so we get that A is equal to V, 31.4, is it 31.4? Yep, 31.4 squared divided by R, which was 0.05, and that gave us a huge A value for A. It turns out to be this number right here. Okay, now that's too many decimals, right? We only want 3 significant figures. But if we round that off, and write it in scientific notation, it's 1.97. Oops, 97 times 10 to the, well, how many times did we have to move the decimal over? 1, 2, 3, 4 times 10 to the 4 meters per second squared. And you say, how do I know this is big? Well, 10 to the 4 is like in the 10,000s. Compare that to what? What do you always compare acceleration to? Gravity. Compared to acceleration, due to gravity, and that's 10 meters per second squared. And so, this number is in the tens of thousands, and this number is just in the tens. So this acceleration that's experienced in these centrifuges is absolutely huge, absolutely huge. And so, like, your blood's made up of, like, say we're separating out blood. Your blood's made up of, like, different types of cells. There's red blood cells, there's white blood cells, there are platelets in there. I don't know all the stuff that's in there. And then there's just plain old fluid, what's called plasma. And all those things are going to separate out. And you go, well, why would they separate out? And that's because they're under so much gravity that the heavier things are going to go to the outside and the lighter things are going to come inside. I shouldn't say heavier and lighter. It's really dense and more dense and less dense. But yeah, that's what's going on. So you get a lot of acceleration in these centrifuges. Okay. So, all right, that's question number 7. Now we have 2 more questions left. Let me see what's going on in the chat there. I'm getting a little bit tired. How about, because these guys are going to take a little while. They'll probably take another half hour and then we're done. I know I could finish it in 2 hours, but I'd like to take about a 10-minute break. Okay, if you don't mind. And so, just go off and do whatever for 10 minutes and I'll be back, okay? If you're watching this later, which a lot of you are going to be doing, you may not even notice the break because I'll just have the time stamps and you could just skip over the break. But I need to get a drink of water, if nothing else, because I've been talking for an hour and a half, okay? So, all right, like I said, I'll be back in a minute. Sorry, in 10 minutes, okay? Exactly 10 minutes. Hi everyone. So welcome back. Let me see. All right, some people still in the chat here. Uh, okay, let's finish off these last two problems and then we're done with our review. Um, they're both projectile motion problems. They're very closely related to one another. As you can see, the language is almost identical. There's just one word that's different between the two, and it's this word right here, above and below. So let's read number 9 and go through it. Number 10 will be pretty quick because we'll be able to use a lot of the numbers from number 9. Okay, so what's the situation here? I'm at the bottom. Sorry, I'm at the top of a cliff 40 meters high. Okay, so there's a cliff and I'm at the top of it, and I toss a rock with a velocity of 10 meters per second at an angle of 20 degrees above the horizon. Okay, in part, so in question 10, the next question I'm going to do, it's the same situation, but I throw it with 20 degrees below the horizon. So I'm not throwing it, like in one I'm throwing it kind of upwards so that it makes an arc up and then down. You'll see the picture in a minute. But in the other one, I'm kind of throwing it downwards. Okay, and of course that makes for a difference. Okay, in the numbers. All right. So, all right, there's a situation, and what am I asking you to find? So, question A is how far does the rock travel horizontally before it hits the ground? All right. Question B is what's its and there's only a question B. There's only two parts. How far does the rock travel horizontally before it hits the ground? And B, what is its velocity just before it hits the ground? Okay. And for B, I'm actually going to ask you. Maybe I should just be explicit here. I want it in polar. Okay, I want the answer in polar coordinates. Okay, let's start off. So the first thing, like always, is to draw a picture. Okay, so let's go to our whiteboard here and start with a clean board. And let's draw a picture. So, whoops, let me switch to no zoom there like that. Okay, and I'm at the top of a cliff 40 meters high. Okay, and a shot's being fired, and I didn't say it lands at ground level, but I think it's pretty obvious from my description. Okay, so here's the cliff, like this, and there's ground level like that. Okay, and in question number 9, here's the rock. All right, now I throw it with like 20 degrees upwards. So it's actually heading off that way when I first throw it, okay? I throw it, and what's it going to do? It's going to go up, 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 and then it's going to come down like that and hit the ground. Okay, there you go. All right. Now, that's the first step. The first step is just, draw what you would see. Okay, maybe just to make this a little clearer, let me just hash this in a bit here. Okay, so this is the cliff here. Okay, that's solid ground down here. Okay. All right. Part B is to draw your coordinate system. All right. Now, on the test, I'm going to have to tell you what the coordinate system is. And the reason is so that the numbers that you get out are the same as, my multiple choice numbers. If you were doing this and it wasn't a multiple choice, you could choose to put the coordinate system in different places. You would get different answers, different numbers for your answers. But once you go to interpret the numbers, you would have the exact same physical situation, okay? Because you move the coordinate system around, of course, you're going to get different numbers out as your answer. But when you go to draw where these things are occurring in the coordinate system, it would always be consistent, no matter where you put your coordinate system. So, you don't have to worry about that because I'm going to give you a coordinate system, but it's good to know that it is coordinate system independent. Now, what I usually do in a situation like this is I ask you to put the coordinate system such that the x-axis is along the ground level like that. Okay, so there's the plus x-axis, and the cannon or whatever is firing the shot is directly above the origin. Okay, so there you go, and this is the plus y-axis up here like that. Okay, and so the origin is right here. I'll put a big circle right there. And so that circle at the bottom here, let me just emphasize it with red, okay? That big circle right there represents, x equals 0 and y equals 0. Okay, so that's the first thing. The next thing is, I guess you could draw it here too. Maybe I'll draw it in red, and that is, the initial velocity. I tell you that the initial velocity is 10 meters per second and at an angle of 20 degrees above the horizon. You might say, well, where's this 20-degree angle in this diagram here? Actually, let me do it in green. Okay, a different color here. So this is where the rock initially is, right there where the green dot is. So if you're at that green dot, the initial position of the rock, and you say, well, which way is the horizon? The horizon would be this way. Okay, parallel to the x-axis. It's kind of like a second x-axis up there. Okay, like that. And the 20 degrees would be right in there. Okay, 20 degrees right in there. Okay, so there's your 20 degrees. All right, it's a little bit small, but I think you can see it. Okay, so now we can start solving the problem. All right, we would begin reading off of that picture your initial position, your final position, and so on. Okay, so your initial position is two numbers. It's both an x and a y value. Let me move that other problem down. Okay, there you can see that. Okay, good. So your initial position is two numbers. Okay, where is it? Well, you're starting off directly above the origin. The rock is starting directly above the origin. So the x value, that is how far you have to move along the x-axis until you're directly underneath it, is 0 meters. Okay, but the y-axis is how high are you above ground level initially. Okay, and that's actually 40 meters. Let's go back to the picture here. So over here, looking at the picture, if you follow my cursor, you know, the x value is like how far do you have to move either this way or that way, that is horizontally, until you're underneath it. Well, the rock is directly above the origin, so the initial x value, x naught, is going to be 0. Okay. The y naught, that's your initial height. That is how high above, y equals 0 are you initially. Well, this is y equals 0 down here. Okay, there's your y equals 0. And how far up do you have to go until you reach the rock? We have to go up to here, and that's 40 meters high. And so your rock starts off at a y naught of 40 meters. Okay, and that's how I got those two numbers. So back over here, just transposing them, the initial x value is 0, the initial y value is 40 meters. Okay, and that's where I first throw this rock. Okay, that's where I'm going to be throwing the rock from. Now, what about the final? Okay, well, the final is, let's look at the diagram again. Okay, the final is going to be down here. All right, when it gets down there. And if you ask me what's the x and y value down there, the y value is easy. It's 0. The x value is like how far do you have to move horizontally to get to that spot, and I can't tell you. Okay, so the x value is question mark. In fact, that's what I'm asking for. Okay, so if we go back to this, what am I asking for in question A? In question A, I'm asking for how far does the ball travel, the rock, how far does the rock travel horizontally before it hits the ground? Okay, and that's unknown. Okay, not only unknown, but it's what you're trying to find. Okay, so there are those two values. All right, so these two are your initial position. These two are your final position. I put a bunch of question marks for x because that's what we're trying to find in part A. Okay. All right. What about your initial velocity? So the initial velocity, I don't give you the initial velocity, but like in x and y components. I give you the initial magnitude, 10 meters per second, and I give you the initial angle. Do I have a theta anywhere here? 1 second. Well, I got to copy and paste my theta from. There we go. So I give you an initial angle, and that's 20 degrees. But if you take a look at that, those two there, they're not in Cartesian, and everything has to be in Cartesian for the equations that we're going to use. Okay, and so we have to convert those to Cartesian, and to convert them to Cartesian, you basically make use of the formulas that we just played with a minute ago. And for your x-axis, for your x component, you just do 10, which is the magnitude, multiplied by cosine of 20 degrees, and that gives you 9.40 for your x component. And for your y component, it's the same formula, but you use sine instead of cosine. Okay, so there you go. You've got your x component and your y component. All right. Remember, this is what I gave you in the problem up here. I gave you the magnitude and I gave you the direction. Now, magnitude and direction are polar, but we're going to need Cartesian, and so we're going to convert them to Cartesian using the r cosine theta and the r sine theta formulas that we used above, and there it is. Okay, so there we go. There's our initial velocity. What about the final velocity? Let's go back to the diagram for a second here. And the final velocity would be the velocity, let me circle it in red here, it would be the velocity down there, okay? Well, in other words, we're looking for Vx and Vy, okay? Now, Vx is easy because Vx doesn't change along the x direction. Okay, the reason it doesn't change is because there's no acceleration in the x direction, and so the x component of the velocity neither increases nor decreases. Okay, the y component changes, and so as a result, we can say that the x component of the final velocity is the same as the x component up here. So I'm just stealing these numbers here. That's going to be the same for the final, but for the initial, for the final x, but for the final y, we don't know. Okay, so the final Vx and the initial Vx are the same. Why? There's no acceleration in the x direction. Okay, it neither speeds up nor slows down. In the y direction, there is an acceleration downwards, so I can't tell you what it's going to be. In fact, that's going to be part of part B. We're going to need this for part B. Okay, so that's going to be a question mark for part B. And then the only other quantities that we need are the acceleration and the time of flight. And the acceleration is purely in the y direction. Okay, there. And I don't know how long this thing is in flight. Okay, so from when I throw the rock and until it lands, there's nothing in the problem that tells me how long it is in flight. Okay, so all right, now what? Well, we've identified those quantities, and we want to plug them into one of these four equations, okay, to get the answers. Okay, so here are the four equations that we can use. These are the equations for 2D kinematic motion, okay, 2D projectile motion. Now, for part A, I'm asking for how far does the thing travel horizontally. Horizontal is x. And so if you take a look at this, you say, well, which one has x information? It's only equation number 4. So we have to start with equation number 4. We don't, equations 1, 2, and 3 have no x information. And so we'll start with equation number 4 to try to get x. Okay, so use 4 to try to get x, okay, the horizontal distance traveled. Okay, so if you're having difficulties interpreting what x is, one more time I'll show you the diagram. So x equals 0 is, I'll do this in red, x equals 0 is here, okay, and I want to know how far does it travel till it hits the ground, how far does it travel horizontally until it hits the ground, and you say, well, how far is this? That is x, okay, so this is x naught over here, and this is x over there like that. Okay, so we want to find x. All right, let me clean up that diagram a little bit. There we go. Okay, let's switch back. So using equation number 4, we have this equation here. Okay, and now we can just plug in the numbers for v naught x. We can put in that 9.4 right there, v naught x, 9.4. So this is 9.4, like that, times t, which we don't know, and x naught is 0, if you recall from up here. So that just drops right out there like that. And you look at this and you go, well, what do I do with that? Because I don't know time. That's right, you don't know time. And so as a result, you're just going to have to leave that for a bit, okay? And you're going to have to now get time. Now you need t, okay? You can get that. Well, you can't use number 4. We just used it. Number 3 doesn't have time. You say, well, can I use number 2? Let's just take a look for a second. So do we have a y? Yep, that's negative 10. Do we have, whoops, I forgot a y there. V naught y, V naught y, like that, okay. Do we have V naught y? Yeah, we calculated V naught y was 3.42. Okay, so we have 3.42. But do we have the final velocity and do we have the time of flight? Well, no, we don't have the time of flight. That's actually why we're trying to use it, trying to use equation number 2. And do we have Vy? Well, no, we don't know what the y component of the velocity is just before it hits the ground. So equation number 2 is not going to do it. We're going to have to get it from equation number 1. Okay? And so just showing you how you can decide which equation to use out of a process of elimination. You can't use that one because that's what led us to equation star in the first place. Can't use that one because it has no time. That one has two unknowns if you try to use it, so you have to use that one by process of elimination. If that one doesn't get it for you, well then there's something, the problem doesn't have enough information. Okay? Okay, anyhow, we're there. And now let's go through it. So y is the final height. This is when it hits the ground, and that should be 0. Okay, so if you go up here, y, the height of the thing when it hits the ground, that's the final position, is 0. Is equal to a half. Ay is the acceleration due to gravity, and it's purely in the y direction, right? It's purely downwards. That's going to be negative 10, like that. And then you have t squared. Okay. And remember, we're trying to solve for t. And then there's V naught y, and V naught y we have right here. It's 3.42. Okay, whoops. Oh no, let's do that again. 3.42 times t plus y naught was the initial height, and the initial height was at the top of the cliff, which is 40 meters, like that. And so there you go. There's the equation that we need to solve. I can simplify that a little bit. All right. And it simplifies to this right here. Oh, one sec. Sorry. Also, I can tell my image is getting a little darker. It's getting darker outside, and my lighting is going up. But that's okay. I don't want to get up and turn on my lights. I don't want to break the flow of the stream. Anyhow, here we are. That's the equation, and simplified a little bit. And you can just identify, the A, B, and C coefficients because you got to use the quadratic formula. And here are the coefficients. So, whoops, A is negative 5 right there. That's the coefficient for your t squared term. Okay, it's negative 5. B is the coefficient for the t term. Okay, the linear term is 3.42. And then C is the constant term, like that. And you can use that equation I told you about in class. That's this equation right here. Sorry, the website. Okay, quadraticsolver.com. And you could just plug in A, B, and C, and it'll give you the answers. Or you could do it the old-fashioned way, whatever you like, and you get these 2 times. Okay, you get those 2 times. And one time is negative and one time is positive, and you wonder, why is there a negative time? And obviously you want the positive time. We want to use t is equal to 3.19 seconds, okay? But you might wonder, why do we have a negative time at all? And you remember I showed you that in class, if I were to extend the parabola back, and I don't know if I have enough room, but let's just see here. If I extend the parabola back here, that red line there, okay? That red line corresponds to negative time. The black trajectory here, that corresponds to positive time, like this. T equals 0 is right there, okay? That's where the rock is initially, and the red is negative time. Okay, that's time before I threw the ball. I know the ball wouldn't have been there, but as far as the parabola is concerned, it thinks that it would have been. And you're asking, really, when is this thing at 0? Right here. And you get 2 answers. You get, it was there at t is equal to, let's see what I got there. T is equal to negative 2.51. So t is equal to negative 2.51 seconds. Okay, at that time, the rock would have been at ground level, but the rock is also at ground level over here, and this one corresponds to t is equal to, what did I get? 3.19 seconds. Okay, so this is your negative time, which is not physically real because the the rock was never there. Okay, but the parabola projects it to being there because the parabola thinks it's like infinite on both sides, compared to the 3.19, and that is the physical time. That is when it's actually at ground level. Okay, so let me clean those up a bit, keep my diagram from getting too messy here. All right, cleaning up. There we go. Okay, let's switch back. Okay, so we're going to use that time. Now, why did we need the time? To substitute into star. Okay, so sub into equation star, like that. And so we have this. And over here, we're going to take out that t, and we're going to put in 3.19 seconds, like that. And that'll tell us how far it travels horizontally. And the answer is 30 meters. Okay, so the rock travels 30 meters horizontally before hitting the ground. Okay, there you go. That is part A. Now, what's part B? Part B was, what is the velocity just before it hits the ground? And I want it in polar. Okay, now to get that, we need both the x and y components of the velocity just before it hits the ground. We have the x component, we don't have the y component. Okay, now we need the x and y components because we need to convert to polar. And so let me get the x and y components first. So here's part B. Part B, we need the x and vy. We already have vx is equal to, and I forgot the number, what was it, 9.4? Yep, there it is, 9.4 meters per second. So we already have that vx is 9.4 meters per second. We need vy. Okay, so you say, well, where am I going to get vy? Well, it was one of the unknowns that we had up above here. Okay, we had it as an unknown for part B. And you take a look at this and you go, okay, well, I need to find vy. And that means you can either use equation 2 or equation 3. Okay, you could use equation 3, but equation 2 is just as good and it's easier. So we'll use equation 2. Okay, so over here, we need use equation 2. All right, and here's equation 2, like that. And now that gives us that vy is equal to -10. The time is 3.19 seconds because that's the time of flight, plus the original velocity in the y direction, the initial velocity in the y direction was 3.42, like that. All right, like that. And that gives us a vy of, what does it give us? It gives us a vy of -28.5 meters per second. Okay, now let's see if this makes sense before we go ahead and convert this to polar. If you take a look at the x component is moving in the positive x direction. The y component is moving in the negative y direction. Okay, let's look at our diagram here. All right, and remember, we are looking at the endpoint right here. I'll just highlight it in red. We're looking at that endpoint right there. Now, which way is the velocity going? Just before it hits the ground. Okay. Again, the parabola knows nothing about the ground, so we have to think just before it hits the ground. Velocity is going like that. Okay, it's going like that. Now, if we put a little coordinate system here like this, like there's your y-axis. So I'm just centering a coordinate system on that point there. Okay, and of course the x-axis is this way. You say, okay, what quadrant is that vector in? It's in quadrant 4. All right, right. So this is quadrant 1 in here. Okay, this is quadrant 2 over there. This is quadrant 3 over here. And this quadrant with the vector in it is quadrant 4. Okay, So it's in quadrant 4, and in quadrant 4, x is positive and y should be negative. Okay, and that's in fact what we found. If we go back here, you'll see that x is positive here and y is negative. All right, now we're still not done. There's a lot of steps to this. Why are we not done? We got the answer in Cartesian, and it's the right answer in Cartesian. Okay, but I asked you to convert it to polar, so we got to do that. Now in converting this to polar, you've got two parts. You've got the magnitude, which you obtain using this formula right here. Okay, and you say, well, did I actually give you that formula? Not exactly in this form. If you look above to where we converted our vectors, okay, if you go all the way back to the vector conversion, all right, you'll see that I had this formula for our vector conversion for x and y to r. And you might compare the two formulas. Let me put them side by side here for you. And you go, well, what's going on here? Well, when we did r, x, and y, we were thinking of like maybe position vectors, and then you've got x, y, and r. But now we're talking about velocity vectors. But they work exactly the same as position vectors. It's just that there's different names for their x and y components. So for the x component, okay, for a velocity vector, we call it vx. And the y component for a velocity vector, we call it vy. Okay, so there's the x and y. For a velocity vector, they're called vx and vy. Okay, vx and vy. All right. And the resultant magnitude we called r, but in this case, the resultant magnitude is v. Okay, and so it is the same formula. It's just applied to velocity vectors rather than position vectors. Okay, so great, we have that. If we now substitute in our numbers, we're going to get this. Okay, so 9.4 squared plus negative 28.5 squared, then take the square root of that, and you're going to get 30 meters per second. Okay, so there you go. This thing is traveling at 30 meters per second. That is the magnitude of the velocity. That's how fast it's going, irrespective of the angle. But now to get the angle, we have to use this formula. Okay, right here. And if you look at this formula, you know, where we had just x and y above, now we have vx, okay, and vy, okay, vx and vy. Again, you know, these vectors have an x and y component, so because we're talking about a velocity vector, it's going to be vx for the x component and vy for the y component. Also, it's in quadrant 4, so we have to add that 360. Well, I shouldn't say we have to add that 360. Again, if you want the answer to be positive, you add 360. Otherwise, you have to interpret the negative answer as being measured clockwise from the x-axis. Okay, but I like adding the 360. Okay, so if you just work that out, you get this. Okay, so 288 degrees. Okay, either negative 71.7 or 288 degrees. Okay, and you go, okay, well, what's that? Can you show me that on the diagram? Can you show me like the 30 and the negative 71 degrees? Okay, so if you take a look at the diagram and you just look at the magnitude, let me highlight the magnitude here, maybe in blue. Okay, so this is just like, you know, how like I'm highlighting it, just how fast is this thing going? Okay, along in that direction, but just how fast is it going? It's going 30 meters per second. Okay, and then you say, well, what about the angle? Because, you know, it could be going 30 meters per second this way. It could be going 30 meters per second that way. I mean, that's a little bit long for that vector, but you got the idea. 30 meters per second that way, 30 meters per second that way. You say, well, which way is it going? Well, it's obviously going in the direction of that red vector there. Okay, so you say, well, how do I measure that angle? Okay, if we start from the x-axis, and let me do this in a purple here, a dark purple. If we start at the x-axis here, okay, and we measure, we turn, that's 90 degrees. That's going to be 180 degrees. That is going to be 270 degrees. And by the time we get to the vector there, that full circle that you're seeing is 288 degrees. Okay, so that's what's going on there. Let me get rid of that circle. All right, so that was 288 degrees. And that was going counterclockwise. If I go clockwise, I'm going to start at the x-axis here, and I'm going to turn clockwise. That is going to be negative 71 degrees, okay? Like there, okay? So it's 71 degrees, but it's actually 71.7 degrees. But in the negative angle direction, which is clockwise instead of counterclockwise, okay? So either you could go around clockwise, so start at the plus x-axis and then go around clockwise to 88 degrees, or you could start at the plus x-axis and go negative 72 degrees, and you'll still get to that same vector. Okay, so that's the meaning of that angle there. All right, did we answer the question? What's the final velocity just before it hits the ground in polar? Yes, 30 meters per second at an angle of 288 degrees to the plus x-axis. All right, great. One more question to go, but this question is actually going to be pretty quick. And the reason it's going to be pretty quick is that it's exactly the same problem, but I just wanted to show you this tiny little variation on it, okay? I'm at the top of a cliff, 40 meters high. I toss a rock with a velocity of 10 meters per second. So far, so good. But at an angle of 20 degrees below the horizon. Below, not above. Okay? And you say, well, how do I picture that? What do you mean by below, 20 degrees below? Okay? So, you know, like horizon 0, if you crank up, you're throwing upwards, that's positive 20. If you crank downwards, that's negative 20. Okay? So we take a look at our picture here. The black line is actually 20 degrees above. 20 degrees below, I'm running out of colors here. Let me try to do it in, well, green is already taken. Let me do it in red. 20 degrees below would be, I would throw it this way. Okay? There would be 20 degrees below the horizon, like that. Now, of course, it's still going to be on a parabolic path, like that, but I think you can see that it's going to hit the ground a lot earlier. Okay? Than it would if you threw it upwards at 20 degrees. So now rather than throwing it upwards 20 degrees above the horizon, I'm throwing it downwards 20 degrees below the horizon. Now the diagram's a little bit busy, but I think you got the idea, okay? You say, well, how do I do that? Like, what changes? Okay? Well, let's take a look. What changes is over here, what's going to change is when we do the values, the x and y values, the x and y components for the initial velocity, that's what changes. Everything else is the same, so I won't rewrite them, but the x and y are going to be different, okay? So you could do this in one of a couple of ways. You can either say v naught x is going to be 10 cosine, and instead of putting in positive 20 there, you put in negative 20. Why negative 20? Let's go back to this diagram here, and that's because, take a look, the red 20 degree angle that I have right in there, okay? Which way am I measuring it? It's negative 20 because it's clockwise. Okay, so I could certainly use a negative 20. The other one is I could do, rather than going around clockwise, I can, let me see if yellow works. Yellow may not show up, but I could try to go around counterclockwise, but then it wouldn't be 20 or negative 20. It would be negative 20 plus 360, in other words, 340 degrees, okay? Now, if you did here cosine of negative 20 or you did cosine of 340, you get exactly the same answer. So here I'm showing that v naught x is equal to 10 negative cosine 20. You could just as well do, instead of 320, instead of negative 20 here, you could do 340, and guess what? You would get the exact same number. You would get 9.40 meters per second, okay? So again, it doesn't matter whether you measure the angle clockwise or counterclockwise. As long as you get the right sign in there, you're going to get the right answer. Now, for v naught y, you might wonder, well, what will happen there? Well, if I put negative 20 in there, the x component didn't change, but the y component does. So 10 sine of negative 20 is actually negative 3.42. Okay, negative 3.42. Above we had positive 3.42 because it was a bit of a positive, it was slightly going upwards, okay, when I first threw it. Here it's got a slight downwards motion when I first throw it, okay, and so it's going to be negative 4.2 meters per second. All right, well, the first question is, how far does the rock travel horizontally? So you proceed the exact same way you did above, but every place you see v naught y, rather than putting 3.42, you put negative 3.42. Okay, so you still start out looking for x, and you'll still get the exact same formula as above. Okay, we still start, with equation number 4 above, and we still have the same uh, um, stopping point because we need t. Okay, and now we're going to look for t, and to find t, we have to use equation number 2. And if we use equation number 2 and we substitute in the numbers, okay, it's going to look like this. All right, maybe I should write equation 2 in there before. Let me go grab equation 2 up here. No, I'm sorry, I said equation 2. I meant equation 1. We still need, so this is actually wrong here. Let me write this in first. Paste that in there. I meant equation 1. Now use equation 1 to get that. Okay? To get time. And so it's that quadratic. We plug in the numbers. This is what's different. That v naught y here, it's negative. Okay? Instead of positive. All right? And then we simplify this, and it simplifies to the following. Well, I don't have the simplification. Let me just write it out for you. 0 is equal to negative 5t squared plus negative 3.42t plus 40. And it's a quadratic again. And up here, if you take like the coefficients, these ones here, okay? Above you had positive 3.4. Here we have negative 3.4, okay? So plug it into quadraticsolver.com, and you will find that your 2 times are these values right here, okay? Whoops, there we go. Okay? So you'll see that it hits the ground in 2.51 seconds. Before, it took, where are the numbers here? It took 3.19 seconds to hit the ground. That's when I threw it up at 20 degrees. But when I throw it down at 20 degrees, it takes 2.51 seconds, which is less. Okay? Now substitute into star, like that. And we get this. For the time now, we have 2.51. And this number is going to equal 23.6 meters. Okay? So previously, it traveled 30 meters before it hit the ground. But now, because we're throwing it down, it's going to be shorter. It hits the ground in only 23.6. Okay, let's look at the diagram, see if it makes sense. Okay? When I threw it and upwards, it traveled along that black line there. Let me just re-highlight it again. So here's the black line. Let me just highlight it in again. All right. And you see how far did it travel horizontally here, like that? And the answer was 30 meters. Okay? But now, when I throw it, and let me highlight it in red again. When I throw, actually, let me clean up a bit here. Let me get rid of it. Whoops, I didn't mean to do that. Okay? When I say how far did it travel this way, this time it turns out to be 23 point, I forgot the number, 23.6 meters. Okay? So you can see that 23.6 is shorter than the 30 meters. Okay, that makes sense because you're throwing it towards the ground more, so it's going to hit the ground in shorter distance. All right. That answers part A. And then finally for part B, we're just repeating all the same steps as previously, so I'll just cut and paste that answer. The value for Vx is still 9.4. Again, there's no acceleration in the x direction, so it doesn't change. It starts off with an x component of velocity, 9.4 meters per second. It continues at that x component of velocity. That doesn't change. For Vy, we can use equation number 2. And there's equation number 2. And I have the wrong number in here, don't I? Yeah, I have the wrong number. I apologize. Hold on here. Why do I have 3. Why do I have 3.1? I don't know. I made a mistake. That's okay. I caught it. Okay, like that. So equation number 2, Just remind you what equation number 2 looks like. Or is it all the way up here? There it is. Make sure I don't make a mistake here. Okay, so here's equation number 2. Vy is what we're trying to find. Okay, A is, of course, negative 10. The time is 2.51. Okay, 2.51 seconds. And the y component is negative 3.42. Okay, it's negative 3.42. Previously it was positive, but now it's negative. Okay, and let me see what that's equal to. I got to recalculate this. All right, copy. It's negative 28.5 meters per second. Okay. All right. And substituting into this. Oh, it turns out to be 30 again. I think I'm making some mistake, but I'm not sure here. Let me just take a look very quickly. We've got 2.5. That should be the opposite of these numbers here. Yeah, they are. Okay, that makes sense. Okay, so I'm good. I'm good up to there. Okay, I'm good up to there. I'm that, and that is good. Let me just make sure that this is, so did that math right. 25.1 plus 3.42. Yeah, this is correct. Okay, it's correct so far. Yep. I don't know why I thought it was wrong, but 28.52. And let me just see what that works out to be. Let's take the square root of that. Turns out to be 30 again. Okay, fine. 30. Okay, so it's still 30 meters per second when it hits the ground. But now, let's see, this one's going to be 28.51. All right, and what's that work out to? It turns out to be the same angle. Okay, it turns out to be the same angle. Yep, because it's the same numbers. Let's go back up here. Yep, it turns out to be the same angle. All right, so some symmetry in the problem. There we go. Okay, it still hits at with 30 meters per second and at 288 meters per second. Okay, so I went a little bit quickly at the end there, but all of the math was kind of the same. The only thing that changes is, just to go back up here and show you, the only thing that changes is this, okay? And I wanted to show you that you could either use the positive or the negative angle there. That is, you could either use negative 20 degrees because you're below the horizon by 20 degrees, or if you want, you could just add, you can always add 360 to an angle. You could add 360 to the negative 20 and use 340. And then if you did cosine of 340, you still get the same number. In fact, you could try it over here too. You could try this on your calculator. Do it both ways on your calculator, and you'll see that if you do 10 sine of negative 20, you get negative 3.42. Or if you do 10 sine of 340, you still get negative 3.42. Okay, either way you'll get the same answer. All right, okay, that ends our review, and let me take a look here in the chat if there were any questions in the chat. There are none. We're down to one person. I don't blame you. This is it's kind of grueling to go through like 2.5 hours of review, but I did everything. Okay, so there you go. Let me just ask in the chat here, are there any questions? Because if not, we'll just end it here. All right, it doesn't look like there's any questions. Okay, this is the end of the stream, and study hard and do well on the test. Bye-bye, everyone.